video to do the extra credit for you. Your test is coming for you in the mail. I could not get this to copy and paste into this particular program, so you'll have to look at your test. This is the extra credit on test 11. All right, the first thing, part A, well, first of all, they give us that table where they tell us the time in minutes and the rate of change of the radius in feet per minute at various times. So we don't really have a function, we just have information about at particular points in time. And then they tell us that obviously the volume of a hot air balloon expands as we heat the inside of it. The radius of the balloon in feet is modeled by a twice differentiable function, so therefore if it's differentiable, we know that it is continuous. R of t, where t is measured in minutes. For time 0 to 12 minutes, the graph of R is concave down. That's going to be important. The above table gives selected values of the rate of change of R prime. Now notice that's not R, that's the rate of change of the radius over the interval 0 to 12 minutes. The radius of the balloon is 30 feet when the time is 5. Okay, the first question asks us to estimate the radius of the balloon when time is 5.4 using the tangent line approximation at time is 5. Is your estimate greater than or less than the true value? Give a reason for your answer. Okay, so what they're asking us to do, this is, we don't have any information for R of t. All we know is that it's always concave down, right? We know that when time is 5, why not? What am I writing on? Okay, this is part A. Okay, it tells us in the problem that when time is 5, the radius is 30 feet. Right, when time is 5, the radius is 30 feet. Okay, the time is 5, the radius is 30 feet. They also tell us from our little table there that the slope of the tangent when time is 5 is 2. So the slope of that tangent line is 2. We know it's always concave down, so I just did a rough little graph there of something that's always concave down, where the radius is 30 when time is 5. Well, what's the equation of that tangent line? It's just going to be y, or r, minus 30 equals 2 times x minus 5, t minus 5, where y, I should really just call that radius, eraser. So the radius, or the y value, is 30 when time is 5. So, and we know the slope there is 2. So the question is, what's the radius when time is 5.4? Well, I could go ahead and change this equation to, something nicer, y equals mx plus b, but I'm not going to because I really like this form. But I'm just going to let time equal 5.4 for right there. So r minus 30 equals 2 times 5.4 minus 5. All right, so that's 4/10. So r minus 30 equals 2 times 4/10, which turns out to be 8/10. So r equals 30.8. 30.8, and our units were feet. So the radius is approximately 30.8 feet. If I just come up in this tangent line, when that's the equation, that's the value of the tangent line at 5.4. So the value of the tangent line at 5.4 is 30.8 feet. So now the question is that approximation too much or too little? Is this more than the true value or less than the true value? And my answer is that's going to be more than the actual value, because the r double prime is negative, or you can say it's concave down. The function is concave down at that point. What that means is all the actual values are going to fall below the tangent. You could use words like that. Since the function is concave down, the actual values fall below the tangent. Okay, so that's part A. We haven't really covered that yet in class, but I was interested to see if any of you could figure that out. That's upcoming. All right, part B you should have been able to get. All right, part B simply asks us, what is dV dt? Well, find the rate of change of the volume balloon. You should understand that that means what is dV dt. When time is 5, indicate the units of measure. All right. So what is the rate of change of the volume when time is 5? Well, from the given, r of 5 was 30. The radius when time is 5 is 30. And dr dt of 5 is 2. That comes off that little table. That's from the table. Dr dt, or r prime of 5, is 2. Since we know the volume is 4/3 pi r cubed, dv is 4 pi r squared dr, dv dt is 4 pi r squared dr dt. So dv dt is going to be 4 pi r squared, r is 30, dr dt is 2. So that's 30 squared, which is 900 times 8 is 7,200 pi. Ooh, that's an interesting pi. 7,200 pi. And the units are going to be what? This is feet squared, right? Feet times feet is feet squared, and this is feet per minute. So that's going to be cubic feet per minute. The AP exam is really emphasizing understanding with units. So make sure you always include your units. And they even tell you indicate units of measure, so you have no reason to forget. But that's 7,200 pi cubic feet per minute. Okay. Part C, our Riemann sum. Yay! Okay. In part C, it says to use the right Riemann sum with 5 intervals to approximate the integral from 0 to 12 of r prime of t. Notice that's of r prime of t. Nope, I don't want that one. No, I want this one. Okay, of r prime of t dt. So that's the area under the curve of r prime, right? You should understand that to be the area under the curve of r prime. So I took r prime and I made a real rough little graph here. Okay, at 0, r prime is 5.7. At 2, r prime is 4. At 5, r prime is 2, etc. 1.2. And 11, it's 0.6. And then, oops, I should label that 12. At 12, I'm at 0.5. Okay. Now, it says use a right Riemann sum with 5 subintervals. Well, since I don't have a function, I can't really take 12 divided by 5. So I have to take the information I'm given. Oh, and also, since they asked for a right sum, that's going to be this one, right? It's not going to be this function off the edge here, right? There's my function. It's going to be the right sum of that. So it's going to be this one, that one, that one. These are getting harder to draw because my drawing's too small here, but it's right there. Okay, so the first one is going to be how wide from 0 to 2 and how tall, 4. Right, so my first one's going to be a 2 by 4, or an 8, plus my second one is from 2 to 5, so that's a width of 3, and my height is 2, so that's 6, plus my next one is from 5 to 7, so that's a width of 2, my height is 1.2, and honestly I'm taking these from up here because that's hard for me to read. Okay, and now from 7 to 11, that's a width of 4, but my right value there is 0.6. Oops, so this should be plus 2.4, plus 2.4, plus, the last one only has a width of 1 and a height of 0.5, so that's another plus 0.5. So 8 and 6, 14 plus, just up here real quick, 14 plus 4.8 plus 0.5, 18, 19.3. So that's 19.3. Now let's talk about the units. Okay, 19.3. This time, this was minutes. Where's my thing? There it is. Minutes, right, by feet per minute. By feet per minute. And the area of that then is going to be feet. 19.3 feet, positive. 19.3 feet. That would be hopefully a little better. So, but the real points for this come from explaining what that means. Using correct units, explain what that means. This means that from, or let me say it this way, in the first, let's see, in the first 12 minutes, F-I-R-S-T, 12 minutes, the radius did what? The radius increased by 19.3 feet. By 19.3 feet. Okay? The radius increased by 19.3 feet. You cannot say the radius is 19.3. You say the radius changed by a positive 19.3, or somehow you make sure you let them know that you understand that that's not what your radius is. That's how much your radius has changed. Okay, now finally the last question, D. D asks, is your approximation in part C greater than or less than the actual value? Well, look at my little sketch here. Is my Riemann sum greater or less than? My answer to this one would be, this would be part D. The estimation is less than the actual value because r prime of t is a decreasing function. And when you take a decreasing function, the right-hand sum is always going to be too little. See that? So for a decreasing function, the right-hand sum will always be too little. You could even include a sketch like this to indicate complete understanding. Okay, enjoy your spring break, but you have lots of work to do.